So welcome to session number 23 in the discrete maths course. So everybody will be rejoicing because there is going to be only one more course session after this one, right before the exam, basically, so after Easter. So what we're going to do today is to start a recap of some of the course material that we've covered. And my original intention was to have this recap guided by your needs. That's why I posted a message on Piazza asking for suggestions as to what you would like to see covered in the recap. Thanks to the single person who has actually replied to this message, we will be starting today by doing recursive definitions and structural induction, which was already on my list of things to do, because experience shows that this is something that people have a little bit of trouble with. Okay, so there's been a suggestion about Gauss-Jordan elimination with reduced row echelon form. So I've noted this suggestion, and we will also do that. In fact, I was planning to do that, especially with unknown coefficients, because that's, I think, something that even people who have delivered very good assignments sometimes have had trouble with. So before we do that, let's warm up by recapping what we were doing last time round so that we don't forget it. And also we warm up with something that has to do with the last part of the course before we go full circle and restart from the beginning. We are not covering 24 lectures in 2 course sessions. So there will only be very few topics that we are going to cover, and we will do so in an example-driven way. That is to say, we are going to solve exercises together. I will introduce the general concepts if and when they are needed. And of course, if you disagree, I'm talking to the people in the room, but also for the people at home, if you disagree, scream. And if you're at home, scream very loud. Okay, so if you might recall that last time round we were looking at something which is called the expectation, the mean or the expected value of a random variable. So what is a random variable, by the way? People in the room are saying, good question. And of course, you people at home are answering this question right now, but I cannot hear you. So I can only hear the people in this room who are telling me that a random variable is 4. I was expecting 42 actually as an answer there. But it could be 4 actually. In that case, it's not very random. In that case, it would be a function from a sample space to the collection of real numbers, such that the value of that function for every element, for every outcome, is actually 4. That's a random variable, where S is one of the outcomes in the sample space. In this case, the random variable would not be very random, but there we are. It is a random variable because it is a function from a collection of outcomes to the real numbers, which happens to be a constant. Okay, in this case, what you would expect the expectation of the random variable x to be? It would be 4. Why is that? Because that's nothing but the sum for all elements of the sample space of the probability of seeing that outcome times the value, the payoff that outcome generates, which is always 4. And now what is this? We can put the 4 on the outside. This would be 4 times the sum of all of the probabilities of the outcomes in the sample space. And now what is this thing in blue? It's 1. Why? Because P is a probability distribution if you sum the probability that one of the outcomes occurs, well, that sum is going to be 1. Because one of the outcomes is going to occur, so the probability you see one of them is 1. So this is going to be 4, because it's 4 times 1 equals 4. But you see, one can learn something even from an apparently simple random variable, which is not random at all. We can use the definition of expectation to figure out, if we really need to go through all the steps, what the expected value of a random variable that always returns 4 is, namely 4. Okay, so let me recap what the definition of E of x is. Well, it's the sum for all possible outcomes of the probability of seeing that outcome times the value of the random variable for that outcome. I'm sort of stammering now. X is the random variable. And in fact, this is what we just used to calculate the thing that I'm now circling in green. Just use this definition. And it will give you that. For this specific random variable that was suggested by your friend. So if somebody asks you what is a random variable, you say it's a function. It's a function from the sample space to real numbers. And what is the expectation? Well, that's the expected value of that random variable, which is nothing but the weighted sum of the outcomes, where the weights are the probabilities that those outcomes actually take place. So suppose I ask you, as I'm going to do now, let's look at a sort of slightly different random variable now. We got a random variable that basically, whose value is the sum of the outcomes of 100 die casts. Okay, I give you a die. You throw it 100 times. What is the expected value of the sum of the outcomes of these 100 die casts? Now, what is the sample space? No, of 100 die casts. Okay, the sample space are all the possible sequences of outcomes that you can get. Then you need to sum them together, but it's a sequence of 100 numbers between 1 and 6. Because each time you throw a die, you're going to get a number between 1 and 6, and you do that 100 times. So the sample space is, okay, the set 1, 6 to the power 100, where the power means take a sequence of length 100 of the numbers 1 to 6, which is nothing but a string. You can view this as an alphabet. And here you're looking at all the strings of length 100 that you can build over the alphabet 1, 6. So 6, 6, 6, 6, 6, 100 times, that would be one of the possible outcomes. Okay, so your colleague is suggesting, okay, you could consider as your possible outcomes the numbers between 100 and 600. In this case, you're doing the sum already. And these are the possible results of the sums, because the smallest number you can get is if you get 1 all the time, namely 100. And the highest number you can get is if you get 6 all the time. So that gives you 600. Okay, so your colleague is saying, okay, so if you look at the bell curve, and now we are doing something that you will do later on in your calculus and statistics course, then it's kind of unlikely that you're getting 100 or 600, because there is only one combination of your values that will get you those outcomes. But let's keep this basic. So there are different ways in which you can define this random variable. Let's take the basic one. Give me a string of length 100 of numbers from 1 to 6, and the outcome, x of applied to that string will be the sum of them all. So x of s is really the sum of the outcomes. If instead I had chosen this to be my collection of outcomes, then x of a number would be that number. Okay, but let's take the basic thing. The outcome of of 100 die cast is a sequence of the numbers that I get. The value of that outcome is the sum of all of the numbers. Now, what is the expectation of this random variable? What is the expectation of this random variable? Okay, Goodney up there is saying 350. And you might say, wow, he's guessing. He's not guessing, and he's right. You know, he's not even an alien creature who performed this mind-boggling calculation using this formula. Aha, one of your colleagues is saying he just calculated the average for one throw and then multiplied it by 100. And the average for one throw of the die is 3.5. Because you say, okay, it's 1/6 divided by 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that happens to be 3.5. Yeah, but why does this work? It does work, and you can see it's a little bit of a shortcut. It's a huge shortcut. You don't want to do this humongous sum over all the probabilities for all of the possible outcomes. Okay, your colleague is saying in the room, because the die casts are independent of each other, but that works for the probabilities. In that case, well, this tells you can multiply the probabilities. There is a property of the function called expectation that actually gives you that this works. Expectation is not any odd function of x, but it's got to do with something that we saw in linear algebra. What kind of function is the expectation? It's linear. In particular, if you have something that is, say, okay, 100 times x prime, where x prime is your random variable, throw the die once and look at the value. This would correspond to throwing it 100 times. Then this is 100 times e of x prime. And the other property of expectation, which we could also have used if we wanted to, is that if you look at the expectation of the sum of two random variables, that's nothing but the sum of the expectations. So if you take the variable value of one die cast and you sum it together 100 times, well, this will give you this random variable that we are considering. And the expectation of that random variable is nothing but the sum of each one of the individual expectations, which we know is 3.5. So it's 100 times 3.5, which is 350. You know, if you had to do it by calculation, you would never finish. not in your lifetime. There are simply too many calculations to do. But since the expectation is linear, you can do it in your head in 1 second and get it right. Because if you really need to sum all those combinations, which are quite a few, 6 to the power 100, which is a sort of slightly large number, 6 to the power 100, well, not only you will never finish in your lifetime, probably, but you will also get it wrong if you finished. And since I'm not really mischievous, the reason why I put a fairly large number here is so that you will not try to beaver away and calculate straight away. There has to be a better way of doing that. Okay, so this was just, you can see it as an advertisement for the linearity properties of expectation, which is the last topic that we covered last time around and the last topic in this course. Any questions about this before we start we restart the course from scratch? Okay, you can view this, what follows from now on, sort of the pill version of the course. I know we all prefer to take vitamin pills instead of eating lots of interesting stuff to get the same effect even better. So let's take the pill for discrete maths 2 course. And then this will be like the matrix. You take the red pill or the green pill. If you take the red pill, you're in trouble. If you take the green pill, you pass the course. Well, you pass the course anyway. Okay, ladies and gentlemen, Madame et Messieurs, meine Damen und Herren, structural induction and recursive definitions. Yoo-hoo! Everybody is really rejoicing. So, what better way than to look at the final exam? This was the final exam from last year that tells you exactly what you can bring with you so that you don't ask me 15 times from now on. You can bring one A4 sheet of paper, no books, one A4 sheet of paper where you can write on both sides whatever you think will be useful for you for the exam. At this point, people ask, aren't you not going to tell us what we should write on the piece of paper? And the answer is no, for one very good reason, I hope. And anyway, that's the reason that I'm going to give you. It's because by preparing this sheet of paper, you will learn a lot. If I tell you what to put there, first of all, I get into trouble if by any chance something that ends up being useful at the exam is not there, which can happen. And second, you don't go through the exercise of going through the course material and figuring out what is it that is important. If you do that, you basically pass the course. Oh, no. So the question is, will we get a separate formula sheet? No. That's your formula sheet. And you know why? Because how many formulas have we actually seen in this course? You know, last year people were saying, wow, I'm not even finished with half of the first page of the A4 sheet of paper, and I've written them all. There are very, very few things you need to remember. The rest is understanding. A calculator. Okay, people say, oh, you don't specify the brand, the year, the vintage, how much battery I should have in the calculator. And you know why? The reason for not specifying all these things is because you really don't need the calculator anyway. It doesn't really matter. The calculator is not going to solve the exercises for you. This also indicates calculations is not what matters. I'm not going to give you a 10 by 10 Gauss-Jordan system to calculate. Why? because it takes the same understanding to do a 10 by 10 matrix and a 3 by 3 matrix. 10 by 10 matrix, you feed it into the computer. I mean, 3 by 3 matrix is just shows me whether you actually understand what you're doing, which is the thing that matters. And it also reduces the chance that you will make calculation errors. 10 by 10 matrix, I will make 100 calculation errors myself. So far, so good. You can complain if you want a big matrix. Small is beautiful. Okay, so there we are. First exercise, which happens to be structural induction over lists. So take out your scratch pad papers, your pens, in whatever color you like them, and let's try to solve together this exercise. Can I zoom in? Yeah, of course, I'll tell you what is in here, but yes, I will make it 200. Perhaps 150 is better, yeah. Let's make it 150. There you are. In this exercise, I give you the recursive definition of the collection of lists so that you don't need to remember it, because this is not about memory. I then define what it means for a list to be sorted, so that no confusion arises as to what it means for a list to be sorted. A list is sorted if you go through the list of the elements of the list, you never go down. You can stay the same, but you can never go down. Okay, the first entry is less than or equal than the second entry, which is less than or equal than the third entry, and so on. And then I ask you to define a function called distinct that takes as input a list and returns a Boolean. And the idea is that this list should take as input, so should be such that if you feed it with a sorted list, then it will return true exactly when all the elements are different. Okay? It will return false otherwise, of course. I say it's exact. And then I give you two examples of what this should do on two specific lists. If I feed it with 155, then it should return false because it has two elements which are the same. If I feed it with 234, then it should return true because there are no two elements which are equal. Note, both of the input lists are sorted. Okay, the function could do whatever gibberish it likes if you feed it with a list which is not sorted. It's only guaranteed to work if you feed it with a sorted list. That's a precondition. Give me a sorted list, I'll behave well. Where behave well means I do what I'm supposed to do. If you feed me with something which is not sorted, then, well, I don't guarantee anything because I was not designed to work on lists which are not sorted. Is it clear what we need to do? Well, let's do it. Like the Nike advertisement would say. And now I just become a scribe for the thinking power of your colleagues in the lecture room. And of course, if you're at home, well, you scribe it yourself based on your thinking power. Okay, so this should be a recursive function over lists. So how do we go about defining it? Base case first. Okay, sort of. Now, the base case might depend on whether the specification said non-empty lists or lists. In this case, it said lists. So the function should also work when its input is empty. I think it said, it didn't say non-empty, but anyway, it doesn't matter. Okay, so your colleague is saying, could I write something like this? This is equal to, oh, not distant. Equals true. Yeah, you need both, actually. You need both two base cases. You need two base cases. Absolutely. Now, this is a shorthand for two definitions. So you could write this. I would be happy with this. But if you want to be completely clear, you just write two. I mean, I live with this happily myself. But for myself, let's write something like this. So in this case, you want to return true. Why is that? Well, because all the elements in the empty list are different from one another. There are no two elements which are equal, so they're all different. Vacuously so. Okay, you only want to return false if you find two elements which are equal. If the list is empty, you cannot find two elements which are equal, so you want to return true. Similarly, if the list only contains one entry, then there are no two different elements in the list. So there are not two equal elements in the list which are at different positions. So you also want to return true. Okay, so these are the two base cases when the recursion actually stops. If there is any problem with this, scream now. Yes. Oh, the question is, have you ever had anybody scream in your class? Not that I remember, but you never know. I mean, not that I remember. I've had people scream outside class, but not in class. Okay, so now for the inductive step. We've dealt with the cases empty list. We've dealt with the case one element in the list. So the inductive step is two or more elements in the list. And now this is where this sortedness requirement on the input list comes into play. Since the list that we get as input is sorted, what is it that this is equal to? Okay, first thing, we want to check whether they're all different. Well, if it happens that the first and the second entry are equal, then we certainly want to return false. Why? Because they are not all different. We found immediately two which are equal. Now, if this doesn't happen, what we know is that since the input list is sorted, we have that M is actually smaller than N. But in fact, we have more. We know more. Can actually M occur in the list L? It can't. It can't, because everything in the list L is at least as big as N, because the input list is sorted. So if M is smaller than N, well, M cannot create any problems for the value of distinctness. Because the list is sorted, things can never go down in value. They can at best grow or stay the same. Since the first element in the list is smaller than the second, it can never occur anywhere else in what follows the second element. Okay, so this is going to tell us something as to how we should do the recursion. Okay, so your colleague is saying, we know that M cannot occur anywhere else, so we can throw it away. But how about N? Yeah, we cannot throw N away. Because what we know is that N is the first entry in the list N followed by L, but possibly N could occur more than once. We don't know anything about the list L yet. So the recursion now says, okay, in this case, I call myself on N followed by L. The fact that I don't throw N away actually allows me to check for the presence of multiple occurrences of N in the list. So this happens if M is different from N, which actually means smaller because the list is sorted. Absolutely. So there are all kinds of variations that you can use in the pseudocode here. So you could have also written this as saying, okay, sort of if M is equal to N, then false, else distinct N followed by L, or variations on this. It's really a definition by cases. If this, then that. And if you have several cases, well, instead of nesting ifs or writing a long switch, I just prefer to do this definition by cases with the braces. Any problem with this? Sort of, are we on the same page? At least for the 20 people in the room, upper bound 20. You know, another thing that the exercise session for the exam said, it gave you 2 examples of what should be returned. Well, if in doubt, check your definition on those examples and see where you get the same result. If in doubt. So for instance here, one of the examples was, okay, if I apply distinct to the list 1, 5, 5, empty, then I should get false because of these 2 occurrences of 5. Well, let's see. Do we get false? Let's calculate. Your colleagues are saying yes, because they are running compiled versions of this, so they run faster. But let's sort of do some hand simulation here. You know, when I was taking my programming course, I didn't have a computer, so I did hand simulation of all my programs, which was a lot of fun, as you can imagine. Okay, so how do we calculate this? Well, basically, we have a list which starts 2 entries followed by a list, so we need to use this clause here in the definition. And this clause says, okay, look at the first 2 entries and see whether they're equal or not. In this case, they are not equal. One is 1 and the other one is 5. So what we need to do is to compute the value of distinct applied to the list once we've thrown away the first entry. So M would be 1, N would be 5, and L would be 5 followed by empty. So in this case, the value of this is the value of distinct 5, 5, empty. Since we didn't find anything wrong with the first element compared to the second one, we just throw the first element away and continue recursively. Well, again, we have a list of length 2 or more. So we need to use the same clause that we just used. The clause says, look at the first 2 entries. One is 5, the other one is 5. They are equal, so you should return false. Okay? So on this example, it works. It doesn't just work on this example, it works on all of them. Okay, so if in doubt whether your recursive definition is doing the right thing, try it on some examples. And if it doesn't work on those examples, well, you know you will need to change the recursive definition. Something is going wrong. Okay, any doubt with this? So by the way, I've also posted some exercises on Piazza, which you can use to practice more. I think I posted about 10 exercises or thereabouts on Piazza yesterday. So they're just meant for you to practice. And in fact, you can practice in front of everyone else if you want. Even anonymously post your solutions so that all of your colleagues will look at them and debug them for you. This is called programming in the wild, or crowdsourced programming, or solving using crowdsourcing to solve the exercises. We cannot do that at the exam, but for training, yes. Okay, so let's do another exercise with lists before we take a break. Let's again consider a function that says let's call it isin, or isin. Takes 2 inputs. It takes a number and a list. And the result should be a Boolean. The result should be a Boolean. So the idea is that isin checks whether n occurs in the list L anywhere. Okay, so it should be isin NL should be true if n occurs in the list, is one of the elements of the list L. Otherwise, it returns false. Okay, so what would be the first thing that you write here? Base case. And base case corresponds to when the list is empty. And in this case, you return false because there's nothing in the empty list, so n cannot be in there. What next? Recursive case. Okay, so if the list is not empty, it has to have what form? It starts with an element followed by a list. Okay, in this case, what is it that you want to return? Okay, if you're in luck and it so happens that n is equal to the first element of your list, then you return true. Otherwise, comment, this means that n is not equal to m, so n is not the first entry in your list. You want to use the power of recursion. If you're checking whether n is in the list and it's not the first element, if it's there, where it should be? In the rest of the list. And how do we find that out? By calling the function recursively. In case you're wondering, in italic writing, M is 3 bumps. It's a 3-bumped camel. And M. After all, I'm scribing for you, so I should pretend to write like a scribe. Okay, any problem with this? So let's do another exercise. And since you're getting bored with lists, let's do a recursive function over strings. Now, over strings of A's and B's. Now, this set AB star is defined recursively by these 2 conditions. Lambda is in AB star. And the second condition says, okay, if X is in AB star, then AX and BX are also in AB star. In other words, give me a string, I'll stick a symbol in front of it, and you can make a longer one. And the symbol can be either A or B because we are considering alphabet AB. If it was ABC, there would also be a clause that says, well, CX is also in there. There was, yes. Oh, the question is the star the same symbol as we are doing regex? Yes, it's actually the same. That's a recursive definition of the set AB star. AB star is the set of all strings that you can write using AB, and you can define it recursively. Yeah, it's the same. It's the same. Oh, in the regex. Okay, so yes. So if you wanted to define this as a regex, then this would be sort of A union B star. Absolutely. Or this. These are all, it's the same thing. But since I'm telling you to, I'm going to tell you to define a function over strings recursively, I wanted to show you how to define the collection of all strings over AB in a recursive function. You start from the shortest string of them all, the empty string, and then you give rules that tell you how to take a string that you've already built and make it longer. And how do you make it longer? You stick a symbol in front of it. Okay? So what I would like you to do now, before the break for me, is to define a function recursively called even A that takes as input a string of A's and B's, and it returns a Boolean. And these functions should be such that even A fed with some string W is true if and only if W has an even number of A's. So if you count the number of occurrences of A in the string, it should be an even number. 0, 2, 4, 6, 8. Now, what I don't want you to do is to use auxiliary functions. So I just want you to define, in a simple way, a function even A, without first defining a function count and then use the result of the function count to determine whether it's even or odd. You don't need it. Okay, the key word here is recursion. Okay, so what is the base case? Even A of the empty string. And the result should be what? It should be true. Because there are no occurrences, 0 occurrences of A in the empty string, and 0 is an even number. 0 is equal to 2 times 0. Okay, so far so good. And how about the recursive case? Well, the recursive case has to take care of strings of the form A followed by X and strings of the form B followed by X. So let's do first the case even A, B followed by X. Okay, does the B at the beginning matter as far as the result is concerned? No, it doesn't. So we can throw it away, which means that the result should be what? The result of calling even A on the rest of the string. Okay, we want to know whether there are an even number of A's in the string Bx. Well, just figure out whether there are an even number of A's in the string X, which is smaller than B of X, so we are fine. Okay, so far so good. Now, what is the other possibility? The other possibility is that the string that I'm fed with, if I'm even A, actually starts with an A. In what case, what is it that I should return? Okay, if I call even A recursively on X, I get true if there are an even number of occurrences of A in X, and false if there are an odd number of occurrences of A in X. Absolutely. So your colleague in the room is saying, well, I just take the negation of even A of X. Why? Okay, because if even A of X tells me true, there are an even number of occurrences of A in X, then if I add another A at the front, that number was even before, I've added 1 to it, it becomes odd. So I should return false, which is the complement of true. If instead even A of X returns false, recursively this means that there are an odd number of occurrences of A in the string X. But now I've added another 1 at the front, so the number was odd before, plus 1, it becomes even. So I should return true, which happens to be not or false. So basically, I want to know whether even A of AX should return true or false. I unleash recursion on the string X, and then I take the complement of whatever outcome I get. Yes, question. Mm-hmm. So the question is, do I mean that this cannot be an even number? What I mean is that, remember, even A applied to any string returns a Boolean. So this thing here that I am underlining in red is going to return a Boolean. This Boolean will be true if in the string X you have an even number of occurrences of A. And it will be false if you have an odd number of occurrences of A. Now, this not here is the Boolean negation operator. So this or that, it depends on how you want to write it. I just write not in plain English. So you take the negation or whatever, the complement of whatever even A returns. So if even A returns true, even AX will return false. If even A returns false, even A applied to AX will return true. And this makes sense. Why? Because if this call returns false, then this means that the number of occurrences of A in X is odd. 1, 3, 5, and so on. But if you add another A then at the front, which is what even AX does, that was odd before, it becomes even. That's why you take the negation. Okay, yes, with a string. So your colleague is saying if you have 4 A's, yes, you would start with true, and then you would have not true, not true, not true, not true. Can we put it in action? Yes. This means that the first part of this session will be longer than for many people like, but yes, let's put it in action. So let's see what happens when I do even A. Instead of taking 4, let's take 2. The principle is the same. Okay? So what this definition says, I take the negation. Let me write it like this so I write less. Not of even A. Now, remember that A is actually the same as A followed by lambda. So I can again apply the same rule that I just applied before to get not on even A lambda. And now I can terminate the recursion because this is not of true. And this is the same as not of false, which is true. Okay? Well, essentially, you start counting. Lambda, 0 entries, even. Then you add an A at the front, odd. Then you add another A at the front, even again. Okay, now everybody is really screaming for a break, so let's take a break.